Welcome to Advanced Geotechnical Engineering course. This is module 7 on Geotechnical Physical Modeling, lecture 8. So, in the previous lecture we introduced ourselves to two aspects which are required for verifying the scaling laws or particle size effects. The one is that modeling of models, or other one is that modeling of prototypes. So, in this particular slide the schematic representation of the figure which is actually used for explaining the modeling of models is given again. So, here on the x axis we have the prototype dimension. So, this can be it can be a footing size, or it can be a wall size, or it can be an embankment size. So, anything in prototype dimensions, particularly at G level is equal to 1, they represent the prototype dimensions if they are in full scale. Then here it is on the y axis on the G level. So, here what we have discussed is that the technique of testing this modeling of models at with the different G levels, and this is basically done with the aim of verifying the scaling laws, is called as the modeling of models. And we also have deduced a number of scaling laws or scaling relationships between different parameters, and they require validity or assure that they follow the scaling laws, and that can be done by using the principle of modeling of models. So, the modeling of models technique is used whenever we are trying to model a new physical phenomenon in the centrifuge, and scaling laws for one or more parameters cannot be derived easily. So, this is applied when we actually try to derive test a model which is a new phenomenon in the centrifuge, and the scaling laws for one or more parameters could not be derived easily. So, if you are having a prototype of say 10 meter dimensions, and we can actually have the the model different models at different gravities, so that they represent all these models represent a prototype which is actually projected here at 1G. Similarly, when you have a particular prototype of 5000 unit size, then we also have 3 different models representing the behavior. So, what does it mean is that it means that if you are having the same prototype with same soil tested with identical boundary conditions, then the performance of these models which are tested model 1, model 2, model 3, and if they are models of this particular prototype, they represent the identical behavior as that in the prototype. So, this is an interesting option for centrifuge based physical modelers for verifying the scaling laws, and also to check the models whether they are free from particle size effects. In case of geo-environmental engineering, whether it is free from the characteristic length effect. So, let us look into the example which is on the test program for modeling of models, this was originally carried out by this Olsen in 1980. This was reported by Taylor 1995, wherein they have tested the test program basically consists of concentric loading of circular footing tests on the circular footings of on a uniform dry sand. So, here the void ratio more or less is actually has been maintained in all the tests as E is equal to 0.565, and the average particle size is between 0.3 to 0.6 mm. So, it can be looked into is what has been done is that the number of models have been formulated, and basically to see where the size effects are there and where the scale effects are going to be there. So, in this particular chart here this is footing dimensions are given on the x axis on logarithmic scale, and here also the G level which is actually given on the y axis. So, this particular line indicates that dP is equal to 0.25 meter diameter footing, and this is 0.5 meter diameter footing, and this is 1 meter diameter footing, and 2 meter 4 meter diameter footing. Now, when you go down from this side, then we can see that the footing sizes increases and the stress levels are different, and when you go in this direction the footing the sizes are same and represent the identical prototype in the field, but they actually have the different G levels. So for example here this particular model tested at 7.1 mm footing diameter is subjected to certain G of 35.4 basically to simulate a 250 mm diameter of footing. Similarly here when we take the 1 meter size, so this 28.3 mm diameter footing subjected to 35.4 to model a 1 meter diameter circular footing in the field. So this particular series of tests which are actually named as series B, F and series C and G and K and D, H, L and P, U, X, these represent 1 meter diameter footings, and the tests J and then tests R which are actually for 2 meter and 4 meter size footings. So for test J, in order to model a 2 meter footing, a footing diameter of 14.2 mm was considered, but the G level is maintained as 141.4. So that means that in order to get TP is equal to 2 meters, what we have to do is that 14.2 mm into 141.4, it yields 2 meter the diameter footing. So the results were actually compared for the prototype footing having diameter 1 meter and all tests corresponding to 1 meter when we see, and the normalized load settlement curves for modeling of models are given. So we know that when we have load carrying capacity of a footing found to depend upon several parameters, and we said that P by gamma D is the principal pi term which actually has to be identical in model and prototype. So wherein we have seen that one particular dimensionless pi term called dg by d, that is which is not similar in model and prototype even in the centrifuge based physical modeling. So in order to see whether to what extent these effects will be there, so in order to verify that, what has been done is that this P by gamma D or which is actually for so this test data is for diameter of 14.2 mm tested at 70.7 to yield a footing of diameter of 1 meter size. Similarly here this is 28.3 mm diameter tested at 35.4 to yield a footing of diameter 1 meter. Similarly here 79.5 mm and tested at 12.5 to yield a prototype diameter of 1 meter. Here also 56 mm tested at 17.7 to yield a footing of diameter of 1 meter. So this can be seen that most of the values which are number of tests have been carried out, and the reproducibility and repeatability of the test was found to be very good, and at delta by D is equal to 0.1 and at P by gamma D is found to be in the range of 95 to 100. Similarly here also at delta by D is equal to 0.1 and with this P by gamma D is found to be in the range of 95 to 100. So these tests indicates that the model actually in the modeling of model holds very good, and also for the type of the size of the footing which is actually considered, the particle size effects are actually minimal or not, it can be said that they are negligible. So here what has been done is that the value of the bearing capacities for different G levels were actually plotted, and the Ovison 1975-79 work is actually compared with Mikasa et al 1973 and Kutter et al 1988, and here it has been found that the x axis has got acceleration field n and bearing capacity is plotted in kilonewton per meter square on the y axis. So the horizontality of these lanes which are actually tested by the several investigators, this indicates that the modeling of the model holds good well. So and then one more interesting thing we need to do is that it is not that all the tests are actually free from scale effects. There are some tests, for example, when you are having say 7.1 mm diameter footing which is almost like the size of a button, then when this footing size is actually supported in a given horizontal line with let us say 0.5 mm diameter is the average particle size, then about 50 number of particles. So in the field, when you have say 250 mm diameter footing resting on the soil in the field, same soil in the field, there are innumerable number of particles are actually going to support the footing. So that indicates that if in order to avoid the size effects, in order to avoid the scale effects, there is a requirement that the footing size, that is d by d50, has to be, they found that has to be in the range of 30 to 180, and if this range is actually maintained, they said that the scale effects particularly due to particle size can be eliminated. So while selecting the dimensions, particularly like a footing diameter, or tomorrow like if somebody is interested in modeling a pile, then pile diameter to the average particle size need to be understood, and if this ratio is found to be having adequately higher number or higher ratio, that is dimension divided by dimension of the particular model, like pile diameter d or footing diameter d divided by d50 has to be adequately large, and then it implies that it resembles the conditions similar to that in the field. So in such situations we can say that the model is actually free from particle size effects. So like this, and this modeling of models was actually applied for verifying the consolidation laws. That means that the time of consolidation, we said that Tm by Tp is equal to 1 by n square. So in that situation, when we actually model the different clay layers of different thicknesses tested at different gravities, and representing the a certain thickness of the layer in the field, then the consolidation or time settlement behavior have to be identical. So this was actually, if we are able to get the identical performance with identical response, then we can say that the particular scaling law, for example for time of consolidation in model and prototype, that is Tm by Tp is equal to 1 by n square, is found to be validated. So and then while discussing the dynamic scaling considerations, we said that there will be a conflict between diffusion and dynamic events, and this is actually arises because the scale factor for the time which is for diffusion is 1 by n square times faster, and that is the time in prototype is 1 by n, time in model is 1 by n square times in that in prototype. So because of this, what will happen is that the excess pore water pressure will not generate to the initial set total stress or the total stress at a particular point. Then what will happen is that there is the partial raise of the excess pore water pressure, and then a rapid dissipation of pore water pressure takes place. But in principle, in the prototype, when you actually really monitor this, it is difficult to get this data, but if you are actually having this excess pore water pressure with time recorded in the prototype when at a location at the onset of say earthquake, then it will have like this, there will be a rise up to a certain level to the target desired total stress, then it will be dissipation. So you can see that the slope of this line is much flatter than the slope of this line, which is actually shown here, and here, and this indicates that this is the curve which we may get if you are actually having the centrifuge model with the model pore fluid. So we said that in order to avoid the conflict, two schools of thoughts were discussed. One is to reduce the gradation of the particle size, the other one is to to replace the conventional pore fluid with water, with a pore fluid having higher viscosity. Then we said that there are a number of different types of pore fluids have been used, and but one thing is that we have to see that the pore fluid will not actually affect the strength properties, and also will not actually alter the constitutive behavior of the soil, and also the damping characteristics, and secondly is that we also have to see that how this is validated or is required. So in this case what we do is that we will have a detailed discussion about a particular pore fluid, and then we will try to verify the requirement of this thing. So from theory point of view, what we said is that this is required, and this actually simulates the situation of the what exists in the field. So once again the qualities of an ideal substitute pore fluid. One is that the density has to be close to that of water, and this is very much required because to have identical effective stresses as that in the prototype. Suppose if you are actually selecting a pore fluid which is actually heavier than water, then for example like zinc chloride solution if we take, then we cannot actually simulate this identicality in the effective stresses, and the surface tension will be same as that in the water, and it should be Newtonian fluid. So where and then also it should be chemically polar and available in it should be available in the wide range of viscosities, and the viscosity should not change with the age of the preparation of this solution, and it should be stable, and its properties should not change in time from the experimental from the time frame of experimental preparation, and easy to manufacture and non-toxic and soluble in water and should be inert. So these are the qualities of an ideal substitute pore fluid. Then number of pore fluids actually have been vogue. The first one to be used is that silicone oil, and classified as hazardous waste and resistant to most solvents, and thus determination of the dry density of saturated soil with silicone oil and the cleaning up of the equipment is difficult, and unit weight is less than that of water, necessitating the corrections to be implemented and relatively expensive. And some laboratories they actually have their own trademark pore fluids, and for that one example is that Technical University Delft, the Netherlands. The composition not known, but evaluated through physical permeability and monotonic and cyclic triaxial, and said that the Delft pore fluid fulfills the required qualities of an ideal pore fluid. Then glycerin and water mixers, which are actually also used, non-toxic and easily mixable with water in any concentration. So different combinations of glycerin and water were actually tried, and this is also one of some investigators have actually used. So in the recent past, methyl cellulose, which is a methyl ether and which is biodegradable and relatively easy to clean up and available in the wide range of viscosities, and unit weight of the solution will be identical to that of pure water, and the components are inexpensive, readily available and not subjected to any proprietary protection. So this methyl ether or a metallose, which is popularly called as, is the pore fluid which is of discussion. So we also said that particularly when we have replaced the model pore fluid, we have there is conventional pore fluid with a model pore fluid having high viscosity, then we actually have said that the permeability will remain same, that is Km is equal to Kp, and when Km is equal to Kp with then Vm is equal to Vp, and with that what will happen is that you have got time in model prototype Tm by Tp is equal to 1 by n. That means that we have slowed down the diffusion event by replacing conventional pore fluid with a pore fluid having higher viscosity. So if you are actually scaling down model by say 50 times, then we need to replace the pore fluid that is conventional pore fluid with a pore fluid having viscosity of 50 centistrokes, because water at a standard temperature it actually has got 1 centistroke the kinematic viscosity. So if you look into this here, the constant head permeability test presented by Divulkar et al. 1999 on sand, which were actually conducted, and then it says that for example water as the pore fluid when it was actually taken, then as the G level increases, either because of the Im is equal to Nip or because of Km is equal to Nkp, which we have discussed earlier, what actually happens is that with an increase in G level the permeability increases. So for water as pore fluid, K increases with G level, and increase was found to be almost linear. And if you are looking for a metallose as a pore fluid, then you can see that K1G whatever we have is found to be equivalent to Kng, and very marginal variation can be noticed. Here the slope of this line is 0.0155. So if you take the inverse of that, you will get as 32. So this was the test which was actually carried out at it should be this marginal differences could be due to the difference in the differences in the preparations of the sample. So you can see that this is the slope of this line is 0.00047 and this is 0.0155. So it can be seen that by replacing the conventional pore fluid with a model pore fluid having higher viscosity, that is particularly here metallose actually has been tried. Then the permeability value, which is coefficient of permeability, was found to be marginal, having marginal variation. So the properties of metallose, in particular the chemical name of metallose is hydroxypropyl methyl cellulose, and it is a water soluble cellulose ether. It is in the form of fine white powder, and metallose is tasteless, odorless, and it is also harmless. And metallose solutions of desired viscosities can be prepared by dissolving certain amounts of metallose powder by weight in warm, distilled and deaerated water. So generally what is done is that the metallose with higher concentration is actually prepared, like for example 500 centistrokes of metallose, and then suppose if you wanted at a concentration of say with viscosity of 50 centistrokes, then it will be diluted by mixing warm, distilled and deaerated water. So metallose solutions of desired viscosities can be prepared by dissolving certain amounts of metallose powder by weight in warm, distilled and deaerated water. So here in this particular chart, the effect of concentration, age on the viscosity of metallose is shown here. So if you see here viscosity, which is actually measured by using viscometer, and the concentration, that is 1%, 2%, 3%. So you can see that with increase in concentration there is an increase in the viscosity. Of course it is not linear, but is found to have a certain variation. But as can be seen here, viscosity when it is actually plotted with age in days, for 1% concentration, 2%, 2.2% and 3% concentration. At 2% concentration itself, the most of the tests which can be done at 50 G can be achieved, and here it is about 75, this is about 75 G, that is 2.2%, and at 203% concentration yields very high viscosity like 200 G. So most of the dynamic centrifuge model tests are carried out between 50 and 75. So it seems that 2 to 2% concentration is sufficient, and another thing is that the marginal variation of viscosity indicates that it can be stable and will not actually alter its viscosity properties with the time, and when we are actually having the ambient temperature of 21 to 24 degrees centigrade. Whereas in the beam centrifuges which are actually there in the world, so what will happen is that because of the cooling systems and because of the ventilation which are actually provided, the temperature will remain in ambient conditions when the the test is in progress. And here the effect of temperature on the viscosity of the model metallose. So here it says that with an increase in temperature, definitely there is a decrease in the viscosity. This is for 2.2% concentration which is shown here, and it implies that if the temperature increases to 40, that means that there is a fall by about 30-40%. However, as said earlier, when we are actually having the suitable ventilation systems in the beam centrifuge equipments in the world, this particular factor is not a worry, because the ambient temperatures will be maintained. So the effect of the metallose on the constitutive behavior of the sand was actually investigated, and then strain controlled CU triaxial compression tests were carried out on water, and 60 centistroke metallose saturated specimens of sand at placed at 70% relative density, the fine sand placed at 70% relative density, and 3 cell pressures of 69 kilopascals, 138 kilopascals and 207 kilopascals were actually maintained. Then here when it is actually plotted with the Q, which is nothing but deviator stress sigma 1 dash minus sigma 3 dash with axial strain, with this particular curve indicates the water as the pore fluid, and this is the 60 centistroke metallose pore fluid. And then here the pore water pressure generation is also shown here for a confining pressure of 16 kilopascals. This is for a confining pressure of 16 kilopascals. So it indicates that the stress strain behavior and pore water pressure generation with water and metallose were very similar. So one thing, the stress strain behavior and pore water pressure generations with the water and metallose were very similar. And secondly, when we plot the Q versus P dash, and Q is nothing but sigma 1 dash minus sigma 3 dash, and P is nothing but sigma 1 dash plus 2 sigma 3 dash by 3, then if you look for 69 kilopascals and 207 kilopascals, with an increase in the confining pressure, the agreement is found to be in good order. But what it actually indicates, that the results indicates that the stress paths are very similar with water and close and found to be better with higher confining pressures, and thus overall the constitutive behavior, that is including the stress strain behavior, pore water pressure generation and the friction angle of sand was not altered significantly by use of the metallose instead of water as the pore fluid. So if a particular new pore fluid is actually being tried, then there is a need to verify the properties, particularly the constitutive behavior of the geometry which is being under consideration, and how it is actually the considered pore fluid, how it is affecting, need to be investigated. So from this the example what actually has been given by Divulkar et al. 1999, it says that the stress paths were very similar with the water and metallose pore fluid, and the overall constitutive behavior of sand was not altered significantly by the use of metallose instead of water as the pore fluid. And further this was actually verified in a centrifuge by using a split container, and the split container actually has got two compartments. One actually has metallose as the pore fluid and other one actually has got water as the pore fluid, and it is separated by a a leak proof separation, and these are the horizontal accelerometer in horizontal direction, vertical accelerometer in vertical direction, and these are the accelerometers in horizontal direction, and these are the accelerometers in water as the pore fluid. These are the accelerometers with metallose as the pore fluid, and these are the accelerometers. These are the pore water pressure transducers. These are the pore water pressure transducers. So here metallose of 60 centistroke kinematic viscosity was considered because the model is at 60 gravities, and the relative density of the type of the sand which was adopted is about 70%, and here basically to subject identical ground motions, this particular type of the split container was used, and a level ground experiment was conducted to demonstrate the importance of substitute pore fluid in seismic centrifuge modeling of saturated cohesionless structures. So here the effect of the pore fluid on the model behavior was actually investigated, and in this particular figure where this side is pore water pressure which is actually measured at 3 different points, this is PM1, PM2, PM3. The locations we are shown once again. PM1 which is at the top, PM2 is in the middle of the container, and PM3 is the close to the bottom of the container. Similarly PW1, PW2, PW3 they are in the water saturated pore fluid. Their PW2 is in the middle of the container, PW1, PW3 are the top and bottom of the container. So when there can be seen that this is the initial vertical effective stress is 18.6 kilopascals. So you can see that the pore water pressure is actually raising up to that level, and you can see here also that you have got 37.2 kilopascals, and the pore water pressure also rising up to this level, and this is with metallose as the pore fluid, but the similar for the similar ground motion, the pore water pressure measured by using PW1, PW2, PW3 are plotted and shown here, and here it can be seen that the rise was actually very small and the dissipation is actually very fast. So you can see that there is a small rise and the dissipation is fast. So when the water actually has the pore fluid, the accumulation of excess pore water pressure was reduced due to high permeability, and however with metallose, due to slower dissipation, higher excess pore water pressures could be generated, and the rate of pore water pressure generation with the rate of pore water pressure dissipation with metallose was considered to be smaller than with water. So this indicates that the pore water pressure generations, the generation as well as the dissipation, the dissipation particularly was actually slowed down because of the the pore fluid, which is actually having higher viscosity than that of water. So here the time histories of the acceleration is actually shown here, and the accelerometers which is actually placed at the close to the top, middle and bottom are shown here, and this is W1, W2, W3 which is in water saturated fluid as shown here. They are distinctly different, but this is the time histories of acceleration which is actually shown. So based on the observations, like it is clear that neither the accelerations nor the excess pore water pressures indicate the occurrence of liquefaction in water saturated soil model, because the excess pore water pressure has not generated to the level to which actually the liquefaction can be attenuated. But here this indicates that if you are actually checking a structure which is resting on in a certain water saturated model, and it is subjected to say tested in a centrifuge, then it indicates that it may lead to conservative results, wherein we actually end up saying that the structure is safe from the liquefaction point of view. But however, in the practice, because of the difference in the pore water pressure generation as well as dissipation, there will be the settlements, and then there will be this lead to a different set of results which actually result in the destruction in the structure. So on the other hand, the metallose saturated soil liquefied completely because the pore water pressure raised to the level of that particular stress, and thus it was shown that the conflict between the dynamic and the diffusion time exists. So that there is the conflict exists, and these results of the seismic centrifuge tests on water saturated soil models could underestimate the consequence of an earthquake. That is what actually we have been discussing, that if you are using water as the pore fluid in seismic centrifuge model tests, then the results can lead to underestimation because of the consequence of an earthquake. So this implies that a substitute pore fluid was actually necessary. The substitute pore fluid is necessary for carrying out particularly the seismic centrifuge model tests. But when we replace the water as the pore fluid, even to saturate a fine sand, a special saturation methods are actually required to be adopted, and then they also take long time for saturate. And if you are actually having layered soil, or if you are having clay and silt, or silt and sand layers, sometimes it is very difficult to saturate with high pore fluids, particularly if you are having a sand with up to say 20-30% fines. There is a possibility that the saturation may take longer time and special methods may be required. But the general methods which are actually adopted schematically are shown here. One is the sucking water into the soil with a vacuum pump. So in this case, a model pore fluid is sucked with the help of a vacuum pump to saturate the sample. And the second one is that in this case a method of saturation with a silicon alloy actually shown. A fluid percolation in a vacuum chamber when actually happens, then there is a possibility that this can actually get the saturation can actually happen. So in order to induce this the seismic turbulence to the models, the schematic there is a requirement of the in-flight earthquake shaking system. So this in-flight earthquake shaking system basically is required to be have high sophistication because we have said that for a model which is reduced by 1 by n times and subjected to n gravities, the frequency has to be n times that in the prototype, and the duration of the earthquake has to be 1 by n times that of the prototype. So this indicates that the in-flight actuating system has to be very powerful and should be able to induce this the earthquake shaking with wide range of frequencies. So in this particular a typical saturated sand with an appropriate pore fluid, which is actually shown here, and the requirement of the one of the other requirements of earthquake shaking system is that the container has to be different. If you are actually using normal rigid containers, so we actually have two types of containers. One is for the static test, the other one is for dynamic test. In case of the dynamic test, with the recent evolution, is the laminar containers are actually evolved, and these are actually used. And so we are going to discuss about why the laminar container is required for the seismic centrifuge experiments. So here the schematic representation is actually shown here, and so this is the basket, and this is the schematic of a typical shaking system mounted on the swing basket is shown here. On this the model which is going to be subjected to shaking is actually placed. So for large equipments, what is actually done is that the shaking will actually happen in this direction. That means that if you are having in this direction, that is perpendicular to the plane of rotation, the shaking happens. So this actually has possibility that we can actually have large models can be tested in a large centrifuges with an appropriate in-flight earthquake shaking systems. So here the HP is nothing but the thickness of the sand layer, which is nothing but n times hm. If n is say 50 g, then it represents about 50 times the hm of the model which is under consideration. So please to be noted that this is a laminar container which is actually required, and this container is actually fixed here, and this depending upon the amplitude model which we are going to do, and these are the the stoppers wherein they actually prevent any detachment of the components at the onset of shaking. So this is the the typical centrifuge shaker during flight. When the model is rotating, this side is the center of the shaft, and this is the the laminar container, and this is the shaking system, and these are the accumulators for pumping oil to the actuator, and this is the basket. So this is actually mounted on the basket, wherein this is actually shown for schematically for 50 gravities. So this implies this is a typical the centrifuge shaker during flight. So first of all, let us discuss what are the different shaking systems are required, and then we will discuss what are the different why a laminar container is required. So in order to have the earthquake shaking, number of ways of have been tried. Generally the earthquake like shaking model in a flight requires a power source or actuator. So the actuator requires high frequency excitation and high forces need to be applied, and the duration of shaking will be very short because the frequency is n times that in the prototype, the duration is short, and actuator must be capped. So in this short duration, the actuator should be able to deliver peak energy flows almost instantaneously, and the centrifuge itself could be subjected to unacceptable dynamic stresses if appropriate reaction masses are not designed into the system. So basically the centrifuge itself need to be safeguarded to prevent any transfer of unacceptable dynamic stresses to the arm and the pedestal of the equipment. The actuator must be compact in size and a minimum mass, and should be able to we should be able to vary amplitude and frequencies contents. Say for example, if we are having a amplitudes of about let us say 0.5 to 1 meter, then we will actually model that let us say 500 mm by at 50 G, something like 10 mm amplitude. So in the frequency content, let us say that the normal range of frequencies which are actually possible in the field are about 1 Hz to say 5 Hz. 5 Hz means very high frequency. Let us say that if we are having a earthquake of frequency of say 1 Hz or 1 cycle per second. So based on the scaling laws, if it indicates that if you are actually modeling at 50 G, then the frequency has to be 50 Hz, and it is subjected to say 10 cycles of 50 Hz or 20 cycles of 50 Hz. So that the sinusoidal motion has to be triggered by a suitable shaking system. So there are the different types of common shaking systems. One of the traditional and old, which is now replaced by University of Cambridge, that is called mechanical actuators, and which was developed by using a simple concept, and a piezoelectric system, which is UC Davis in USA, and electromagnetic system, shaking system in Shimazu centrifuge in Japan, and hydraulic actuator in University of Colorado, USA. So this is bump in road indicator system, wherein the bumpy road actuator was actually used. So what has been done is that the profile actually has been preset on the periphery of the centrifuge, and the landing is activated, and it moves along this set profile which is there, which is shown here, in the picture onto the the centrifuge chamber vertical wall. And earlier traditionally this was actually used to study the earthquake motions in the University of Cambridge centrifuge, but nowadays this has been replaced with a very powerful actuator. Now before looking into the different types of requirement of the containers and then shaking systems, let us look into the example problem. Consider that we have got a small volume which is 3 into 10 to the power of minus 2 meter cube, is subjected to say 100 gravities, and the equivalent volume is nothing but 3 into 10 to the power of minus 2 meter cube into 100 cube. Then let us say that this is actually subjected to 10 cycles at a frequency of 100 Hz and with an amplitude of 1.5 mm. So the time in model is about 0.1 seconds, that is 10 by 100 is 0.1 second. Similarly, in the equivalent in the prototype is that 10 cycles at a frequency of 1 Hz. So because the frequency is 1 Hz, which actually model at 100 G, so the model frequency is 100 Hz, the same motion, but it is actually having 100 Hz frequency, here 10 cycles at 1 Hz frequency. So the acceleration from the the deductions we have made, that is amplitude into 4, this is the acceleration term in the equation which we have derived, where 1.5 by 1000 into 4 pi square into 100 square. So with that what will happen, this is the frequency, with that what it actually says that 592 meter per second square, it is 60.3 G. Similarly the acceleration in the prototype is 0.15, that is amplitude, into 4 pi square into 1 square is 5.92 meter square, that is 0.6 G. So this is 1 G, and so this is lateral acceleration is about 0.6 G. So if you know the unit weight of the soil, then by multiplying 592 meter per second square into the mass of the the mass which is actually subjected, we can actually calculate the lateral force, that is due to the size dynamic force due to this mass into the acceleration. So another thing which what we can try is that we have discussed that if you are having the velocity of moving particle within the model, if it is actually let us say that say less than 0.05 times the model velocity, we said that Coriolis effect can be neglected. But if it is in the ratio of 0.05 V to 2 V, we said that the Coriolis effect cannot be neglected, then models have to be designed to safeguard against the Coriolis effects. And if the velocity is say more than 2 times model velocity, we said that the Coriolis effect can be neglected, because that is very fast event. Example is that the throwing of ejecta due to triggering of a charge. So let us check for Coriolis effect for the same dynamic model which you have tested, and V is equal to 30 meter per second. So with that what we can say, we can calculate by velocity by using velocity magnitude term, which is nothing but am is equal to 2 pi fm, and wherein the amplitude, that is 1.5 into 10 to the power minus 3 in meters, 2 pi into 100. So with that what we have got is that 0.94 meter per second, and firstly let us check whether it is less than 0.05 V. So 0.05 into 30, so about 1.5 meter per second. So hence this is we can say that for the dynamic model here, whatever we have done, the error is actually 6.2%, which is less than 10%. So the dynamic model under consideration where the Coriolis effect is negligible. So like this, if you are actually having any particular model, dynamic model, the Coriolis effect can be the presence or can be checked beforehand. So this problem, what we have done is that we have done a model which is subjected to the shaking, and then we actually have calculated also whether the Coriolis effect is negligible or what is the error due to Coriolis effect, that is actually has been calculated. So now let us look into the typical shaking tables which are usually available in different parts of the world, and this is a camshaft shaking table which was actually developed for inducing the shaking to the models. And this is electromagnetic shaking system which is actually which works on the principle of AC coil and DC coil. So you can see that this is the T-shaped plate which is fixed here, and with excitation of AC coil and DC coil, the shaking table actually is subjected to this is the the seismic excitation. So but one demerit of this electromagnetic shaking system is that the system actually is the payload is very high. So that means that you cannot actually take large models subjected to, because electro shaking system itself will be very the self weight will be very high. So because of that the payload which can be mounted on the shaking table will be limited, and also the the broad range of frequencies are also limited. This is another electromagnetic shaking system which was used at Shimazu centrifuge in Japan, and this is typical hydraulic shaking system at Nishimatsu centrifuge, wherein it has got 2 servo valves, and that is the black color one which actually indicates the shaking table. So this is the in-flight shaking table system at Tongji University in China, wherein this is after Ma et al. 2006, where they actually mount the models on this shaking table. So this is in-flight shaking table at Korea Water Resource Corporation, KOWACO, where it actually has the payload of 1.5 tons, about 15 kilonewton, and maximum shaking acceleration is about 45 G, and shaking forces about 350 kilonewtons. So very high, and shaking frequency range is 6 to 350 hertz. So it actually has got a wide range of frequency band, and so this is a type of shaking table which is actually used in Korea. So after having seen the different shaking systems, let us look into the boundary effects, particularly when you are actually having earthquake modeling experiment. We said that when you are actually having a static container, that is the container, that is rigid container which is used for say centrifuge model tests, then there can be possibility of multiple reflections of waves at the onset of earthquake motion. So the centrifuge models are generally enclosed with finite boundaries provided by a model container, and the artificial boundaries of the model container may distort the stress and strain fields and generate P waves among other superfluous wave reflections in the model, and that are not present in the prototype. So in the prototype when the typically you will not actually have the reflections because of the infinite boundaries, but in the model, because of the confinement with very stiff walls in the model container like in rigid container, there can be generations of P waves and also the reflection of the other superfluous wave reflections. So the realistic boundary conditions at the boundary of model produce accurate model simulations of soil seismic behavior, basically that reflect the behavior observed in the semi infinite soil layers in the field. So now consider, so this is what actually has been discussed. When you are actually having in the prototype, you actually have got, when it is subjected to say certain ground motion, and because of these infinite boundaries there is only the secondary waves are generated. But when the centrifuge model with a rigid container is used, because of the seismic excitation, there is also the generation of P waves, the compressional waves, and also the other superficial waves which actually causes the multiple reflections. So which may affect, which are actually going to affect the, let us say a particular structure being studied can be a possibility of leading to the misinterpretation of results. So this is typically the way how it is there in the prototype. So you can say that when it is subjected to a certain type of motion in this direction, so there will be a deformation in this direction. This is the element before deformation, this is the element after deformation. At the you can see that at the center and along the edges you actually have got identical deformations, and then also there is at all points actually the soil stiffness, dynamic soil stiffness is identical in this direction. So and also there exists actually some conjugate shear stresses, and the sigma V, this is vertical stress, and sigma H here, this is at the element A, which actually has got the stresses like this, sigma vertical stress and then horizontal stresses. When we are actually having a rigid container with a smooth wall, so what we have is that the absence of the shear stresses can be noted here, and the reflection of waves causes, see at the center the deformation may be identical that as that in the field, but however the edges actually has got, when the model is actually shaken in this direction, subjected to shaking in this direction. So the soil column deformation at the edges is actually different. So this actually can be noted. So the deformations is they are different, and also the absence of the conjugate shear stresses or complementary shear stresses. So if the end walls are smooth and stress dissimilarities would occur because of the lack of complementary shear stresses on the elements at A and B. So particularly when you are having a rigid container, there is a possibility that the rigid container actually having very high stiffness as compared to soil. In principle in the prototype the stiffness is actually identical, so that causes also a problem. So this was actually resolved with a number of different other options which were tried, like some of the earlier containers were like ESB type containers, wherein the aluminum and rubber alternate packing systems were used to induce some flexibility to the side walls of the container. But however in the latter stage the laminar containers actually have been developed, and these track ring devices originally developed for simple shear tests have been increasingly used to simulate the free boundary conditions in earthquake modeling of soil deposits, and this type of container is actually called as a laminar container. And the design concept of laminar containers is that the container should have a limited contribution to the response of soil system, and it should not cause the reflection of the waves. And laminar containers are constructed by stacking lightweight rings separated by bearings that permit relatively free movement of the soil and the rings during the shaking. And this also these laminar containers are actually found to simulate the actual behavior in the field, so that it induces the the so called the identical deformations at the edges as well as in the center. So this is a typical laminar container. What you can be seen that when the model is actually subjected to shaking, and this is a pile which is actually being subjected to some shaking. So you can be seen that like in the field the deformations are actually identical, and then lead to the motion which is analogous to that in the field. So, in this particular lecture we try to understand about the again the concept of modeling of models, and then we also try to see why what is the necessary and how the the replacement of the pore fluid can be justified with replacement of conventional water fluid can be justified by using modeling of models experiments, as well as the experimental evidence which we actually have said that there is a requirement for dynamic centrifuge experiments, the replacement of the modeling of the pore fluid is required. Then finally we have also seen that different types of shaking systems which are actually in vogue, and then the laminar containers which are actually used for the dynamic equipments, so that this actually simulates the identical behavior of the prototype in the centrifuge models, particularly the dynamic centrifuge experiments.